CS161, lecture number 13, cookies at CSRF, announcements. I realize it's better if you hold your nose. Okay, so these are basically the same announcements as yesterday. The midterm grades are released on Gradescope. If you spot an error in grading, that happens all the time, so feel free to submit a regrade request and we can take a look at your answer and change your grade if necessary. I think we mentioned this also. Discussions for today are canceled, just so we can get back on schedule, but office hours are still on, so feel free to stop by. The Project 2 Design Doc draft is due next Wednesday. So again, Project 2 is a design project. You have to design a secure piece of code yourself. And our advice to you is to start by designing. So don't worry about Go code just yet. Just worry about designing for this week. Get your design in. If you have some help, if you want some help, feel free to stop by office hours and you can talk about your design. And then once you have your design draft ready, then you can start implementing. Someone asked, is there a deadline for regrade requests? We talked about having one, but honestly, I don't really care. As long as you submit the regrade request before the end of the semester, it'll probably be fine. So yeah, personally, I don't like the idea that, oh, if you miss a deadline, then we can no longer fix our mistakes. So if you ever catch a mistake, feel free to just let us know. But it would be good if you could let us know sooner so we could fix your grade sooner. And then there's homework, and that's due July 19th, Monday. And that homework, again, is mostly Project 2 warm-up. So it's kind of to get you ready for and start thinking about how Project 2 works. Okay. And then there's an optional lab. So if you feel like having some fun with crypto, that's something you can try out. It's pretty simple. There's not too much code you have to write. And it's due the end of the semester. So feel free to tackle it whenever you have time. Okay. So yesterday was the first web lecture. So most of it was just, let's talk about what is the web, how does the web work? And the first thing we talked about are URLs, which are a string that uniquely identifies a piece of data on the web. So the web has a whole bunch of servers serving a whole bunch of different files and services, and the URL uniquely points to a single piece of data. And the URL has several parts that we talked about, right? There's a protocol at the beginning that tells us which internet protocol to use, and we'll talk about those later. But the ones you have to know are HTTP, which is the one we study, and then HTTPS, which is a version that will be secured over the internet later. So that will make more sense later, I hope. And then there's location, which tells us there are a whole bunch of web servers on the web. Sorry, I mix this up sometimes too. But the location says there are a whole bunch of web servers on the web, and we have to pick one. So the location uniquely identifies one web server, and sometimes it contains a username or a port, which identifies an application on that web server. So maybe it has several applications, and I pick one. And then once I know which web server I'm talking to, I have a path which tells me which file on the web server to fetch. So this web server is hosting lots of files and services. The path lets me pick one. And then optionally, I can add a query which says, if I want to request an interactive service from the web server, so I want the web server to actually do some computation for me. So I want Google to perform a search for me, for example. I need to give Google my search query. And to do that, I will supply an argument in the URL so that Google's server can process my argument and perform the search and then give me my search results. And the fragment is optional, but sometimes you use it by the browser, so I wouldn't worry about that too much. And we talked really briefly about how special characters should be escaped. So for example, question marks are special characters in URLs. So if you want a question mark in your URL for whatever reason, you do have to escape it. Okay. Then we talked about HTTP, which is a protocol used to retrieve and request data. So again, you could just say, well, forget it. If I want to request data, I'll just send the web server a blob of bytes, and then the web server will just return me a blob of bytes. But that seems really messy. So we have a couple of rules in place to make things a bit more organized. So in particular, we have the HTTP request, and the request has a couple of fields. It has a method which says either I want to get information from the server or I want to post information to the server. So usually get doesn't change state on the server, post does change state. And then we have to give the URL path to figure out which file on the server we want. And if we want to perform some function, then also some query parameters. And then if we're making a post request, we're asking the server to change some information, so we probably have to give it some data. So a post request might be, if I'm on Twitter, I want to post a tweet, so that would be a post request, and I would send the tweet in the data. A GET request might be, I want to see this person's feed, so I make a GET request with no data, and then the feed is returned to me, so that would be GET. And then we talked about how the HTTP response is structured. So there's a status code, which tells us what happened. So was it a 200 okay? Was it a 404 not found? Was it a 403 forbidden? What exactly happened with our request? Did it work? Did it not work? And then some data if the data is returned to us. So that was HTTP. And then we talked about a web page itself has lots of different parts. So the data that comes back to your browser can be displayed to you and in nicer ways than just plain text. So HTML is a language used to create structured documents. You can make links, forms, images. You can even put websites inside other websites if you want to do that. And then we talked about CSS, which is a language to make your websites look nicer. So you can define colors, effects, animations, whatever you want. And it's pretty powerful. And then we talked about JavaScript, which is a programming language for running code in the browser. So again, the server does not run JavaScript. It has the JavaScript code, and then it sends the code over to us over HTTP. And then we receive the code in our browser, and then we run the JavaScript code ourselves. And JavaScript is very powerful because it can basically modify any part of the web page that it wants. It can also create pop-up messages to annoy the user, or it can also even make its own HTTP requests, which we will see later today. And then finally, we talked about our very first web security policy, and this is the same origin policy. So we said, well, it would be a problem if I had two browser tabs open. One of them was at evil.com, and the other one was at amazon.com, and I was shopping for whatever product on Amazon. I don't know. And it would be a problem if evil.com could access my amazon.com data. It could see my password, it could see what I'm purchasing, it could make purchases by itself. That would be a problem. So we have to define a way to separate browser tabs. And so the rule enforced by the browser is if you have two different websites open and they have different origins, they're not allowed to interact with each other. And what we mean by origin is the set of protocol, domain, and port. So again, all you have to do is look at the protocols. If they match, okay. Look at the domains. If they match, okay. Look at the ports. If they match, okay. And if they all match, then the websites have the same origins, so they can talk to each other. So if I have like two Amazon tabs open, it would make sense that I would want, if I updated the cart on one side, I would want the other side to also update. But if I had websites with different origins, like evil.com and amazon.com, they should be separated. And so that's what the same origin policy says. And finally, there were a couple of small exceptions, like if I'm running JavaScript, that actually runs with the origin of the page that loads it, even if I load it from some other website. We also talked about how websites can display images from other origins, but with a very limited functionality. And then websites, if they want to, they can agree to allow some very limited sharing if they want to. Okay, that was all last time. Now today is all about cookies and CSRF. So yesterday, someone asked a very good question, which is, if I'm browsing around the web, how can I keep track of things like logged in status or customization statuses? And that's basically what all of today is about. So we'll talk about cookies, the policy for setting and sending cookies, and how you can use it for session authentication. And then we'll go over our very first web attack, which is CSRF, and then talk quickly about defenses. So that's the goal. We'll see if it all fits. I don't know. Okay, so here's cookies. So again, HTTP is a request response protocol. What this means is you send one request, you get one response back. And the reason why it's designed like this is because every request basically looks independent, right? So if I make 10 HTTP requests, I get 10 HTTP responses, and the server basically processes each of those independently on its own. So it has no idea that these requests are connected or anything like that. So they're all independent. That's good, but it has a problem because a lot of modern web stuff should be customized. So for example, if I'm on some website and I have to have dark mode, and A lot of people are very dark mode sticklers, and I show them how I use Slack on light mode. I get a lot of angry DMs. But if I want to enable dark mode, I would like future responses to also be in dark mode. So if I say enable dark mode on Slack, and then I make some requests to the Slack web server, even though those requests are all processed independently, Slack has to somehow understand that these are dark mode requests and return to me a website that's customized to look dark, right? So that's a customization that I might want. Or maybe if I log into a website, I want future responses to be related to my account. So if I'm browsing my email and I log in once and I make some requests like open this email and send this email, I would like all of these requests to be associated with me and my email account. Right? So these are all requests and responses that should not be processed independently, or we want them to not be processed independently. But HTTP by itself can't do that because HTTP is a one request, one response protocol. It has no functionality for associating multiple requests with a single person. So all it sees is one request, one response over and over and over again. So we have to add something to help us customize a request. And that thing is called cookies. So I actually don't know why it's called cookies now that I think about it. I don't know why there are so many food related things here. We had hashes, cookies, and like pancakes, but whatever. Cookie is a piece of data that's used to maintain state across multiple requests. So it solves exactly what we were just talking about. If I have multiple different requests and I want some state to be maintained across those requests, that's what the cookie is for. So how do I create a cookie? There's a lot of different ways. The server can tell me to create a cookie. So the server can return in its response a special header called set cookie. And what this does is it tells the browser, here's a cookie for you, you should store it. And the browser will be like, okay, it's a cookie for me, so I'll take that. You can also create cookies with JavaScript. So maybe the website returns some JavaScript and the JavaScript runs some code, it creates a cookie. And you can even create your own cookies in your browser. So if you feel like it, you can open up your browser settings and create your own cookies. So there are lots of different ways to create cookies. Now, who stores the cookie? So it's the web browser who stores it, not the web server. So again, the server can give you a cookie or you can create your own cookie, but they're all stored in the web browser. And as you might expect, I guess, the storage is called the cookie jar because it has cookies inside. So that's how you store them. And finally, how do you send them? This part is a little bit weird. So we'll talk about this a lot, but basically the browser will actually automatically attach relevant cookies in every request. So you as the user don't have to say, well, I'm making a request to Amazon today or Google today. So I want this cookie, this cookie, this cookie. I don't want this one, I want this one. You don't have to do that. The browser will automatically do it for you. So I don't think anyone here has tried to browse the internet before and had to like manually select cookies, right? The browser will automatically do it for you. So you never actually notice this unless you know what cookies are. And so we have to define what it means for cookies to be relevant, and we'll spend a lot of today talking about that. But the idea is the browser will pick for you which cookies need to be sent, and we'll send those for you. And the ones that are unrelated to your request, the browser will not send. And the server now can use those cookies to customize your responses and chain together a bunch of related requests. So for example, maybe you have a cookie for dark mode. So I tell the server, I want all my requests to be in dark mode from now on. Show me dark mode. And so what the server will do is the server will give me a set cookie response that says, here's a cookie for you. It says dark mode. So it's a dark mode cookie. And in the future, if I ever make a request, what happens is my browser will always send the dark mode cookie off to the server. So every time I make a request to this server in particular, I will always attach the dark mode cookie, right? The browser will do that for me. And the server will always see, here's a request. Oh, it has a dark mode cookie. So I'm going to make this page dark and give it to this dark mode obsessed user. So that's how sending and storing cookies works, right? So your browser stores the cookie that says dark mode. And every time you make a request, you send the dark mode cookie off. And the server understands, oh, this is from someone who wants dark mode. So it will black out the background and all that and then give it to you. Any questions on how cookies work? We'll talk lots more about this, so no worries. Okay, so what does a cookie actually look like? So the cookie actually looks like this. So you're staring at one right now. It doesn't look very tasty, but it is a cookie. So the actual data in the cookie is a name value pair. So you have a name, you have a value, and that's the actual content of the cookie. And these can basically be any string, although some special characters can't be used, like a semicolon. And I think you'll see that in project 3. So that's a mental note for you later. So for example, right, here's a name, the name is theme, the value is dark, so that might be a cookie for dark mode, right? Someone asked, what's the difference between a cookie and a cache? That's a good question. I believe the cache is for local browser storage, and it's usually for performance, right? So maybe I'm going to make the same request to a website like 10 times, and I don't want to have to wait for the server to load the same website to me 10 times because maybe my internet's slow or something. So I think the cache is usually for performance, so that reloading websites over and over can be a bit faster. So if I know that I have to fetch a Google logo, I may as well store it in my cache and just pull it from my cache, I think. So it's mostly for performance if you're talking about the browser cache. But the cookie is not for performance, it's actually for correct functionality or for extra functionality. So I believe that's the difference. But yeah, cookies aren't quite caches because they are not just there to help speed things up, they're actually there to provide extra functionality. That's a good question though. So anyway, name value pair, there it is. The next thing is domain and path. So these are these next two. So the domain and path are going to help us with our problem before where we said the browser automatically attaches any relevant cookies. What does it mean for a cookie to be relevant? How do I know that this cookie is relevant for this website but not for this website? That's what domain and path are here to help us with. So we'll talk about these a lot more, but basically these will help us define which requests should this cookie be attached with and which cookies or which requests this cookie should not be attached with. And as you might expect from yesterday, the domain attribute looks like a domain in the URL, and the path attribute looks like a path in the URL. So we'll see this later. But these two together will help me determine if I make a request to this website, do I need to send this cookie? And the browser will look at domain and path and figure it out. If I make a request to this website, do I have to attach the cookie? The browser will figure it out for me. And finally, there are two security ones that are useful if you care about security. So these are called secure and HTTP only, which is kind of a confusing name, but we'll talk about it. So these two attributes are either true or false. So there's no data inside, you just pick true or you just pick false. So if the secure attribute is true, then what we're saying is this cookie can only be sent over HTTPS, the secure version of HTTP, the one where the internet connection underneath is secured by cryptography, which we'll see later. So if it's just regular plain old HTTP where the data is just sent over the internet with no encryption, no integrity, then this cookie will not get sent. However, if the internet connection is secured with HTTPS and there's cryptography going on, and that helps us protect against internet attackers, then this cookie won't be sent. So if you have a cookie that has maybe some secret information inside, you might want to set the secure cookie, the secure attribute to true so that this cookie isn't sent over insecure internet connections. Then there's one called HTTP only. This does not mean that it's only sent over HTTP and not HTTPS. That's what the name would make you think, but it's not really that, which is kind of funny. But, and by funny, I mean deeply confusing. Please fix your naming, people. But the HTTP only attribute says the JavaScript in the browser is not allowed to access the cookie. So basically, you can only access this cookie with HTTP or HTTPS requests. So if you're sending it off to a server, that's fine. But if some JavaScript is trying to read this cookie, that's not okay because JavaScript is not HTTP. So those are the two security attributes, and I'm going to get water, so you can ask questions. Okay. And then finally, there's one last attribute, which is the expires attribute. So cookies don't last forever, as in real life cookies don't last forever, and web cookies also don't last forever. So you have to have some expiry date. The fun has to end eventually. And at some date, this cookie will no longer be valid. And this is usually a timestamp. So for example, this one is August 12th at 8 p.m., which is a time you might be familiar with. I don't know. And then This is usually a timestamp, and if it's in the past, so if this timestamp has passed, then this cookie is officially expired. It's stale. Do not eat it, or else you're going to have stomach problems. And the browser is going to delete it from the cookie jar. So the browser will realize this is a stale cookie. I don't want to keep stale cookies around, so I'm going to throw it away. Okay. And again, whoever sets the cookie has to decide all of this stuff. So if the server is sending me a cookie, it's going to decide all of this stuff for me. If I'm setting a cookie myself, I can decide all this stuff myself, but it usually has to be set by someone. So that's all the parts of a cookie. So now you've seen the cookie, you know what all the parts are. There are some other fields, but they're not as important, so we'll leave them out. So now we can finally talk about cookie policy. So here are some issues, I guess, before we talk about that. So for before, we remember that the server can include a set cookie header and give me a cookie. So server says, cookie incoming, catch. And I catch the cookie in the response, and I put it in my cookie jar. Then the browser will automatically attach relevant cookies. Again, here's this word again, relevant, that we haven't defined yet, but we're about to now in every request. So we have to figure out a way for the browser to automatically determine, is this cookie useful for this request? Is this cookie useful? Is it going to affect my security if I send this one? I have to figure it out. So there are some security issues if I get this wrong, so I better design this correctly. So for example, a server shouldn't be able to set cookies for unrelated websites. That would be a very big problem if evil.com got to set a cookie for google.com. That would be kind of strange, right? Because now maybe evil.com is a notorious dark theme hater, and evil.com says, here's a cookie for Google that's going to set everything to light, to light scheme or light theme. And now all my Google requests are suddenly light theme, even though I never set them myself. That might be a problem. So I don't want websites to be able to set cookies for unrelated websites. That doesn't seem like the right thing to do. Another thing is I don't want cookies to be sent to the wrong websites. Maybe I have a secret cookie for authenticating a user, or I have a cookie with some very private data inside, which we'll see later. I don't want this cookie with private data to be sent to evil.com. I only want this private cookie to be sent to Google because I'm using it to log into Google. So I need to be very careful about where I send cookies, because if I send a cookie to the wrong website, things can go horribly wrong. So those are my issues. And now we're going to design a policy keeping these in mind so that none of this gets violated. So this is called cookie policy, and this is all stuff enforced by the browser. Why? Because the browser is the one sending these cookies. So it's the browser's job to figure out what to send, what to accept, and so on. So there are two main questions we have to answer. The first question is, if I receive a cookie, so the server says, here's a cookie, catch, should I take the cookie or should I throw it away? So that's the first thing I have to figure out. Is this cookie a legitimate cookie, or is the server trying to poison me? Like, what's going on? And also, if I'm making a request to the server, do I attach the cookie or do I not? So these are the two questions we have to answer. Now, cookie policy is not the same as same origin policy. These are two different things, which is a little bit confusing. Same origin policy is for having two websites open at the same time and seeing if they can interact. Cookie policy is all about your cookie jar and what to accept from the cookie jar and what to send out from the cookie jar. So they're actually not quite the same, which is a little bit annoying, and it leads to some very obscure web attacks, but that's what happens when you don't design with security in mind, and now you have to add all these random policies at the end to make everything work. So good job, web people. So before we do that, we have to really quickly go back to domains because they're going to come up a lot. So remember, the domain in the URL came after the double slashes, but before the next single slash. And what it looked like was it was a bunch of words separated by dots. So piazza, that's a word. Com, that's kind of a word. And there's a dot. So phrase is separated by dots. And it turns out, because of this dot separation method or structure, I can actually draw out the directories or the domains into like kind of this hierarchy, right? So here's like dot, which is the smallest domain you can possibly have, just a single dot. And then I can say .edu, .org, .com, right? I can say piazza.com, google.com. It's kind of what you'd expect. You can draw a tree out. And notice that the hierarchy is always separated by dots. So I go .com and then I go piazza.com. That's separated by dots. So here's an example of a hierarchy. So we go from root to .edu to berkeley.edu to eeks.berkeley.edu. So a couple of things to note here because they're going to come up later. There's something called a top level domain. So these are the ones that are directly below root. So these are the very broad domains. So like .edu is a top level domain, .com is a top level domain, .org, .co.uk, I don't know, some other countries, right? So these are all top level domains because they are just below the root and they span a huge amount of websites. There are so many different .edu websites. And one of them is berkeley.edu. And within the berkeley.edu domain, there's something eeks.berkeley.edu. So we usually call this a subdomain, so you'll see that come up sometimes. But the main thing to note here is the top level domain just below root. Okay. Now that we know that, we can come up with our cookie policies. I'll level with you here, maybe because Nicholas is not here, so I can get away with this, I don't know. But cookie policy is kind of boring. Past lectures, you tend to spend a lot of time on like making sure you internalize this, but my personal opinion is that this stuff is boring. This is some rule that the browser has to figure out every time, and the browser is sitting there running this little check every single time you make a request. It's very boring, in my opinion. So my advice to you is I would not try to internalize and memorize this cookie policy. What I would do is I would write this on my cheat sheet and follow the rules, because if the browser with the little code can follow this rule, then you can follow this rule too. You just have to follow the rules. So to me, this is like reading a book of law or like reading a rule book, which is like, yeah, sure, I can do that and think about why the rules are useful or interesting. But I would much rather do something else. So let's just talk about the rules really quickly. And I assume once we're all done, everyone's going to write this on their cheat sheets and we can all go home and just follow the rules. Okay. So here's the rule. It's kind of annoying. So here we go. The server with a domain of X can set a cookie with domain attribute Y. So remember, the cookie has a domain attribute, right? We saw the cookie had a table and there was a domain attribute inside. That's the domain attribute, that's red. The server itself also has a domain. If the server is giving me a response and telling me to set this cookie, the server has a URL, right? Everybody has a URL. So this server has a domain and it's giving me a cookie with a domain attribute. So it's very easy to mix these two up, but they are two different things. So the server with this domain, that's the URL of the server, can set a cookie with this domain attribute, that's the domain attribute inside the table, if these rules apply. So here we go. The domain attribute is the domain suffix of the server's domain. Oh, that's so many words, I hate it. Okay, but let's think about it. There are some ways that I thought of that makes this easier. You can either think X ends in Y, or you can think X is below Y on the hierarchy, or you can think X is more specific than Y. Those are all valid ways to think about this. So that's how I think about it. And if you're using this one, which says X ends in Y, make sure to check domain by domain. So because we're working in terms of domain hierarchies, it's not okay to say like ley.edu ends, or you can't say berkeley.edu ends in ley.edu. That doesn't work. You have to match everything in between the dots. So you can say berkeley.edu ends in .edu, true, but you can't say berkeley.edu ends in berkeley.edu. That doesn't work because you didn't match in between the dots. So if you're using X ends in Y, just make sure to make a note of that. But all these are valid ways to think about this. You can think about the hierarchy. You can think about, is this domain more specific? You can also think about just doing some string matching and think, does X end in Y? Those are all valid ways to check this. Again, to me, not very exciting, but yeah. And one other thing you have to check is that the domain attribute Y is not a top level domain. So that's too crazy, and we'll talk really quickly about why later, but you can't do that. And finally, the path attribute, nobody cares, just accept it. So there's no restrictions on that. So here are some examples. Let's try to follow the rule book. So let's practice a little bit, I guess. Here's a domain, mail.google.com. This is the server's domain. So the server is the mail.google.com server trying to ask me to set a cookie. So mail.google.com is throwing me a cookie and saying catch. Do I catch it? Do I just let it fall on the floor? What do? I follow the rules and I take a look at the cookie domain. So this is inside the cookie. It says this is a google.com cookie. So I just check the rules. I say, does X end in Y? Well, mail.google.com does end in google.com. Makes sense, right? And I match between the dots. So I see Google matches Google, com matches com. I'm good. I can also say X is below Y on the hierarchy. So if I drew the hierarchy out, I would see that mail.google.com is below google.com if I drew out the table. Or I could say X is more specific than Y. So mail.google.com is a more specific domain than google.com. As you can see, they're all the same thing. Just pick whatever works. And the last thing we have to check is that the domain attribute is not a top-level domain. So this is not a top-level domain. A top-level domain is something like .edu or .com. This is just google.com, so I'm good. So I followed the rules. It was very boring, but I got it, and I understand that this is a cookie I can set. Isn't that fun? Let's do another one since you're also excited. Google.com can set cookies for google.com. Why? Because this blue thing, X, ends in this red thing, Y, or this is below this on the hierarchy. I guess I should say below or the same. And this is more specific or the same compared to Y. So that's okay too. And again, check that this is not a top level domain. Yes, good, and we're good. Okay, very cool. So someone asked about Y, and we'll talk really quickly about Y later, but let me just give you one last one. Can google.com set cookies for this? Well, you might think yes, because, well, this google.com ends in com, so that seems okay. Problem, com is a top level domain, so this actually is rejected. So that's all exciting. Now, if you want the reasoning behind it, I'm honestly not even 100% sure because modern domains sometimes are a little bit finicky, but basically, I think you can't set things for more specific domains, or rather, like Google can't set cookies for a more specific domain like mail.google.com. I guess the idea is because, like, I don't know, maybe like the google.com server has a bunch of different services. You can imagine maybe like mail.google.com is managed differently than maps.google.com or images.google.com. So maybe you want some sort of separation, I guess is the best I can come up with. But again, it's not that interesting. And if you follow the rules, things will work out. I will say one that's kind of interesting is you don't want to set cookies for domains that are TLDs, which kind of makes sense because, as we'll see later, if the domain is a TLD, this cookie will be sent to literally every .com website. That would be horrible, right? Remember how we said back in cookie risks that cookies shouldn't be sent to the wrong websites. So it would be terrible if a cookie was sent to every .com website ever, because there are so many different .com websites, that would be a problem. So there is a very good reason why you can't use TLDs, because I don't want a cookie that be sent to every .com website ever. That would be way too broad and it's not useful. Otherwise, I think it's just something people came up with when the web was being designed. So yeah, fun. Put it on your cheat sheet and let's move on to more interesting pastures. Okay. So how do we send cookies? We have to answer this too. So we figured out if someone gives me a cookie, do I accept or not? I just follow the rule book and figure it out. Do I send a cookie? Again, I have to follow the rule book. And the rule book says there are two things you have to check. The domain attribute is a domain suffix, blah, blah, blah. The path attribute is a prefix, so many words. Okay, I'll give you a save here. So here's what I do. Here's the server URL. So my browser is making a request to this URL in black. Makes sense? I'm making a request to this person. In my cookie jar, I have a cookie. This cookie has this domain and this path. Domain's in red, path's in blue. Remember, the cookie has a table, it has a domain and path attribute. These are the attributes. So this is the cookie I'm wondering, do I send, do I not send? I'm trying to figure it out. This is the URL that I'm thinking about whether I should send it to. So one kind of quick hack that I like to use is I just do this. I take the domain, I take the path, I put them right underneath the URL and I line everything up. And all I do is I check, do they match? Oh, they match. Okay, I'm good, I send. Do they not match? Oh, I'm not good, I didn't send. That's basically all you have to do. So isn't that fun? And remember, by match, we mean match in between the dots. So it would not be okay if the domain was like s161.org, because s161.org, maybe it matches cs161.org, but it doesn't match in between the dots. So it's not okay. But if you line up the single slash here, and then you just kind of branch on both sides and everything matches, then you're good to go. And if they don't match like they don't here, then you're not good to go and you don't send it. And that's basically it for sending cookies. And as you can see, if the domain was like a top level domain, so if this was like a .org cookie, that would be terrible because it would match every .org website. That would be a problem. Okay, sorry, that was definitely boring. But again, rules are rules. We got to follow the rules. And so these are the rules. And again, all these rules are here to do for us is basically, remember how we said the browser sends relevant cookies? This is what it means to be relevant. It's this very boring definition. Okay. And again, we also have to decide, when someone sends me a cookie, are they trying to attack me? And if they are, I don't want to accept this. So that's what the previous thing was about. Okay, those are the rules. Let's talk about more exciting things. There's a whole section on attacks. I don't know if I have time to do this though. Let's see. It is 417, so I probably don't. This attack is kind of fun, but it's definitely the most complicated attack we will ever, I think that's ever in the slides. It's so complicated that it goes on and on and on and on. So we will probably talk about this later if we have time. Okay. Or you can read it by yourself, but it is very complicated. It's like web plus memory safety mashup. It's quite a lot. But yeah, let's just skip over to session authentication, which I think is kind of fun. So we've talked about cookies. Cookies let us save any sort of state we want. There's in particular one very, very important set of states that I would like to save. So yes, dark mode is excellent, and I would love to have dark mode. That's one way of using cookies. I can also use it to customize my request or whatever. The one very, very important use of cookies, maybe the most important, is if I'm logged in. There are so many websites these days where you have to log in, right? You got to log into Google. I got to log into Facebook, Twitter. I don't know. I guess there are lots of different places you have to log in, right? And Cal Central, I don't know. And the idea is if I'm logged in, I don't want to have to log in for every single request. That would be horrible, right? And when I'm logged in, I make lots of different requests. So if I'm checking my email, I open lots of emails when I'm checking my email because I'm very popular. People love to send me emails and fan mail, so I have to check all of my mail, and that takes a lot of requests. I have to open mail from this fan and this fan and this fan and this fan, and I have to do it for a lot of different requests, right? And remember, the requests are all independent, so the Gmail server has to know that all of these requests are from me, and it's me trying to open them. This logged in user, not the other users, right? I don't want it so that anybody can open this mail. It has to be me, the logged in person, who can open them. And then when I'm done, I want to log out so that future requests are not associated with me. So the easiest way to do this, if I was, if I didn't care about users, was I'll just say, every time you make a request, type your username and password. So as I'm opening mail, for every single email I open, I type in my username and password so that the Google server knows it's me. That sounds kind of awful, right? Now, every time I have to open an email, I have to type my password. That's pretty horrible, right? Or if I'm like in Cal Central and I have to navigate stuff, I have to type my password every time. That's terrible. So is there a better solution? Is there some way the browser can, I don't know, can it like save some state for me? And this was supposed to be kind of like a very philosophical question, but because I didn't animate any slides, the answer is right there. You use cookies. So let's do that. And so we don't have to type our username every time. So here's the intuition. The way I like to think about this is concerts. So I don't know if anyone has been to a concert in the last year, but if you do go to a concert, the way it usually works is you enter the venue. So what you do is you wait in line and you show up and you give the doorman your ticket and your ID. So here's my ticket, here's my ID. The doorman checks them. So yeah, this is a good ticket. I scan it. This ID is good. You're 21, you can drink. And then they let you in. But before they let you in, they always give you something, right? They give you that wristband. So you have to keep a wristband on your wrist as you, go into the stadium. And you're like, wait, why do I need a wristband? And the reason why is because, well, let's say I forgot something in the car or I want to go use the bathroom or whatever. So I have to leave and come back. Now, I could, every time I come back, wait in line, show them my ticket and my ID, and let the doorman rescan my ticket and check my ID again. That sounds very annoying. So what do? Is I leave, and when I come back later, I just show the doorman, I have a wristband, you got me already, and they just let you back in. So you do not have to represent your ticket and ID every single time you go in and out. Isn't that nice, right? So that's kind of the idea behind session authentication. This is basically wristbands, but on the internet. So the idea is exactly the same, but the web version. So here we go. The session token is this secret value. So instead of a wristband, it's a secret value. And we're going to use it to associate requests with an authenticated user. So the first time you visit a website, this is like when you're waiting in line and you get in the first time, you have to show your ticket and your ID. That's your username and your password. So you do have to show them one time because they have to know that you're valid and then you can get in. If these check out and everything is good, you receive a session token. Okay. And the server will remember this session token is you. So the doorman, this one doesn't quite work in real life, but maybe the doorman remembers, oh, the person with the pink wristband is Payron or something. I don't know. But the server will associate you with the session token, and it will do so in like a database or something. Now, in the future, every time you have to make a request, you no longer have to retype your username and password because that would be horrible. Instead, what you do is you attach the session token on the request. The server checks the session token, sees, oh, this is this person's session token. I know who that is. They've already given me the username and password. They're good to go. And now they know that this is your request. It's not anyone else's request. It's yours. And notice now you do not have to re-enter usernames and passwords. That's nice. And so session tokens are implemented with cookies. So again, cookies can be used to do a lot of different things. You can use it for dark mode. You can customize whatever. But one way to use cookies is session tokens because the model fits so well. So one more time, the first time you visit the website, you make a request, you give the server your username and password, the server checks those. If it's good, the server gives you the cookie. So it says set cookie this with a session token. And the session token is some random value. And the server associates, oh, this user is currently being associated with this token. So it makes this mapping in its database. Now, when you make a request, remember how the browser automatically attaches cookies? So the browser will automatically know that, oh, this request is going to Google, and this person is logged into Google because they have the session token cookie. So it will automatically attach it for you. Server checks the token, sees, oh, that's a request from this person, right? It looks in the database, says, oh, this request is from this token, which is this user. So it knows it's you, and you do not have to retype your password. That's great. And then when you're done, if you want to log out, or if you've been logged in for too long and you're automatically kicked out, then the browser and server just deletes the token and you're back to where you started. So that's how you do session tokens with cookies. Any questions? So it's kind of cool, right? So this, to me, is way more interesting than cookie policy. Cookie policy was like, oh, I got to follow the rules. Rule 1, rule 2, rule 3. But this is kind of cool because now I figured out this clever way to avoid re-entering my username and password by taking advantage of cookies. So that to me is very cool. But because we're dealing with people who are logged in and not logged in, we have security to deal with. I don't want other people to be able to log in as me. That would be a problem. So this session token is very sensitive. If an attacker steals my session token, they can basically log in as me. Because think about this, right? If the server, so when we make a request, the server just checks the session token. If it's there, they know it's you. If someone steals your session token and makes a request with your session token attached, the browser will think that's also you, even if it's the attacker. So it's very important to not have your session token stolen because it's the only thing identifying you. You already got the username and password done, so this is what's identifying you. So if an attacker steals it, they can log in as you. Big problem. So the server has to make sure the session tokens are random and secure. The server should not do something like the session token is the timestamp. That would be horrible. Now the attacker can guess the session token. Or the session token is generated, like, I don't know, as a hash of the username. That would be terrible because everyone can hash the username. So those would be bad session tokens. What I want is I want very random, very hard to guess, very secure tokens. I also have to make sure that other websites can't just come in and steal my session token. So if I have evil.com open and I have amazon.com open and I'm logged into Amazon, so I have a session token for Amazon, I don't want the evil.com website to just come in and steal my Amazon token. That would be bad. So the browser has to enforce isolation, and we talked about this already. We use cookie policy, we use safe origin policy, so that these malicious websites can't come in and steal my cookies and my session tokens. And finally, the browser shouldn't be able to send this token to the wrong website. That would be very bad, right? I don't want, if I have a session token for google.com, I don't want this session token to be sent to evil.com because it's a session token for Google to log into Google, why would I just give it to the attacker? That would be horrible. So the cookie policy makes sure that I don't send session tokens to the wrong websites. So this is all stuff you have to be very careful about because session tokens are very sensitive. Okay. Now, a session token is a cookie, as we've described before. So what attributes should the server set? There are lots of different things you can try out, right? So the name, probably just call it token or something. I don't know. The value should be random. We talked about this already. Now, what about all these other attributes? So we can think about them. So the domain and path have to be very carefully set so that the cookie is only sent to requests that require authentication. So if I set these incorrectly, maybe I'm suddenly sending this cookie to too many people or not enough people. That would be a problem. So I need to carefully set these so that this session token, very secret value, is only sent to requests that require authentication. And if request doesn't require authentication or is to an attacker or something, I don't send this cookie. So I need to be very careful when I think about these. And secure and HTTP only are security attributes, so it doesn't hurt to make them true. Maybe let's say secure has to be true so that I'm only sending over secure internet connections. That seems like a good idea so that network attackers can't steal my token. HTTP only could be good so that JavaScript can't access my token because JavaScript maybe doesn't have to. And expire depends on when you want the cookie to expire. So maybe I say that if you're logging into a bank, I want to kick you out after 15 minutes so that you're not, so that if you leave the computer and come back, someone won't, log into your bank or something. So the expiry date is up to the server, but something might be like, after 15 minutes, this cookie is no longer valid and you have to log in one more time just to make sure it's still you. So those are all things you can set and adjust yourself. But in general, I would say definitely keep the security attributes true because security is good. Make sure that these are carefully set, and then depending on how long you want the user to stay logged in, pick an expiry date. Okay, that takes us to the end of session authentication. Do we want to break? Do we not want to break? What do people think? Should we just do like a 2-minute, like a 3-minute break? Because there is a little bit more cookie break. That's a good idea. Okay, let's do that. Okay, we're back and some doodle magically appeared. Interesting. So we talked about cookies, we talked about session authentication. Now we can finally get into an attack that you can do on these policies. It's called CSRF, cross-site request forgery. So really quickly, as we talked about just now, session token cookies are used to associate a request with the user, and the browser automatically attaches cookies in every request. We talked about those a lot. So how is this vulnerable? Well, what if the attacker tricks the victim into making an unintended request? So the attacker somehow convinces the victim to make a request that they did not want to make. Well, what happens is the browser automatically attaches the relevant cookies. We've talked about that. So the browser will have no idea that the victim didn't intend to do this. The attacker will think the victim meant to do it. And so the victim's browser will just automatically toss out the cookies. And what will the server think? The server will think this must be a request from the victim. Even though the victim didn't intend to do this, the attacker tricked the victim into doing all this, the server will actually think it's a request from the victim. So it's kind of simple. All you have to do is just trick the victim into making a request. Because cookies are always automatically attached, they will just be attached onto the unintended request, and the server will have no idea of telling that this was not a legit request. This is it basically. So there are lots of variations, and we'll talk about how it works, but the very baseline definition of cross-site request forgery, or CSRF, is literally just all you do is you perform an action as the victim by tricking the victim into doing something. And because of how cookie-based authentication works, the victim will automatically attach the cookies, and the server will think it's from the victim. That's it. That's CSRF. We're done. We can go home, except not really. So let's talk a little bit more about it just to kind of dig in. So the usual process is we authenticate to a server. So this is this login step here. We give the server our username and password. The server gives us a cookie with a session token. That's how session authentication works. So the user knows the token, the server knows the token, but you know who doesn't know the token is the attacker. Because look at this login arrow, it's between the server and the user. The attacker has never seen this token, which makes sense. The attacker has no idea what the token is, so they can't log in as the user. All is good so far. Now here comes the attack. The attacker tells the user, hey, psst, make this request, right? So it tricks the victim into making this request. If the user doesn't know what they're doing, they're like, okay, I'll make the request. And the user makes the request, so here it goes. And remember, what does the browser do in this request? It automatically attaches the cookie. So this malicious request comes over to the server with the cookie inside. The server sees the session cookie with the session token and thinks, oh, this is a request from the user. It has to be from the user because they sent it and they have the cookie and nobody else has the cookie. So the server will just happily accept the request. And now the attacker has tricked the user into doing something because the user automatically attached the request or the cookie in the request. So that's CSRF basically, and we're done. Except maybe the step 2 should be talked about a bit more because someone might be like, how do I even do that? How do I trick this victim like this? So let's talk about that because this step is a little bit weird. There are lots of different ways to do this. So let's separate the request into GET requests and POST requests. So let's talk about GET requests first. The easiest way to get someone to make a GET request is to click a link. GET requests don't have any data inside, remember? So HTTP requests are GET or POST. And because GET requests are not intended to change state, there is no data inside the GET request. It's just the URL and that's it. And the category of GET. So all the attacker has to do is tell the victim, click this link. And the victim's like, okay, I'll click it. And if the link goes to this GET request, then this GET request is fired off with the cookies. So maybe you make a GET request to bank.com/transfer $100 to Mallory. That seems like a very nasty, unintended request. But this link will have the cookies attached in the request, and the bank.com will think that this was a legit request from the user. So if you want to be a bit fancier, you can also open an attacker's website with a link. So the user clicks on the link, it opens an attacker's website. The attacker's website has some JavaScript, and the JavaScript makes the request because, as we said yesterday, JavaScript can make malicious requests. So that could be another way, right? Lots of different ways. Another way that's a bit clever, if I don't want to just ask the user to click on something, how about this? There's a website that the victim will visit. We know this victim will visit the website. So maybe like a web form or Facebook or something, right? And what do, right? I put some HTML on the form. So how many people still use web forms? Does anyone still use web forms? So web forms were these like message boards where you posted like messages and people replied to your messages. Very interesting and old. But basically everybody could put their own HTML on the form because it's a message board. So what you do as the attacker is you put some HTML on the form like this. And when the victim visits the form, so they don't even have to click on your link or visit an attacker's website, they just go on the very malicious or the non-malicious form. So they browse normally, go on the form. They haven't done anything wrong, right? They just go on the form. And what happens on the form? The form contains this funny HTML tag. It says image source equals this. That's not an image. But what do we know about image tags from yesterday? Well, the image tag says go to this URL, fetch the image, and show us the image. And to go to this URL, I have to make a GET request to this URL. So what happens is the user loads the form, they see this HTML tag, and the browser immediately makes this GET request with the cookie, and the user has just been CSRF'd. Is that a word? The user has just been CSRF'd without even knowing it. They didn't click on a link. They didn't go to the attacker's website. They just went on a normal forum or Facebook or something, and they immediately got hit with CSRF. Oops. And this will probably return an error because that's not a picture, but too late, the GET request already got sent off with the cookies and everything is bad. So these are some ways you can get the user to make a GET request. These are all valid ways to do it. And one thing you might notice is, remember how we said GET request should not modify state? This is a very good reason why GET request should not modify state, because this is a GET request that we're assuming modifies state because it's transferring money. And because it's modifying state, now the attacker, all they have to do is do any of these, and that causes the victim to be CSRF'd. So GET request that modify state, probably not a good idea, and here's one reason why. Now that's GET request. What about POST requests? Now POST requests are a little bit different because, like we said, you have to include data in a POST request. So in fact, if you type something in your browser, you actually cannot make a POST request. Like if I click on a link, that's not a post request. If I type something in my address bar and hit enter, that's not a post request. Those are all GET requests because there's no data inside. A post request has to have data inside. So ways to make post requests include submitting a form or clicking on a button. So those are ways to make a post request. Now, turns out clicking on a link still kind of works, but you have to be a little bit cleverer this time. Now you do have to open an attacker's website with the link. So make a GET request to the attacker's website. The attacker's website has some JavaScript, and the JavaScript makes the post request for you. So the clicking the link still kind of works, but you can't directly click on a link to make a post request. You have to go to the attacker's website and create some JavaScript, right? Or we can do the second strategy again. Remember how we said you can put something on a website the victim will visit? So let's put some JavaScript on a website the victim will visit. So maybe the victim will visit a form, and on this form, we put some JavaScript on there so that when the victim visits the form, they run the JavaScript in the browser, and the JavaScript fires off a post request. Right? You can even be more evil and say, here's a legitimate website. I pay for an advertisement on the website, and the advertising has JavaScript inside. That's another way to put my JavaScript on a legitimate website. And again, if the victim visits the legit website, the JavaScript will run, and now they've made a post request. So here are ways you can get the victim to make a post request. So even if you use post requests for requests that change state, that's a good strategy, but it still doesn't stop CSRF because all of these things can still happen. So you're not clear yet. Okay. Here's a slide. If you remember this one from like the memory safety unit, we talked a whole bunch about there are different software weaknesses. And we remember how we checked off like out of bound write, out of bound read. We checked off use after free, all those. Well, today you got another one. It's called CSRF, and it's right here. It's actually in the top 10 of 2020. So this comes up a lot, and it's good to know about it because it is still all over the web. Yeah, it's there. So be careful about it. It's a very relevant attack, and we'll talk about more of these later. So stay tuned. Okay, there's a blue slide. I'm going to skip because I don't have that much time, but you can see in YouTube there was a way to CSRF on YouTube, right? You force the victim to make a request, and the attacker could do all sorts of things with the requests, right? This slide is kind of funny. When I encountered it when I was fixing the slides, this slide is absolutely ancient. I mean, like some of this stuff, I don't even know if it still exists on YouTube. Like, do you still have like friends and family on YouTube? I don't know. This was a very old slide, and for some reason it's still here. So enjoy the classic YouTube slide. But basically the takeaway is if you use CSRF, you can force the victim to do lots of different things. Here's another one, also kind of old, but this CSRF attack actually happened on Facebook. So this happens to big companies too. And what did they do? You see here, HTML image tag. That sounds familiar. What did they do? They did this. Here's the HTML image tag. So that attack actually successfully hit Facebook in 2009. And anybody who opened a Facebook page with a comment on a Facebook post with this HTML image tag immediately gets CSRF attacked. So yes, this happens to big websites too. Okay. And yes, the attack elegantly ends with a valid image. So I think what they did was so clever that this image tag actually not only did it make a request, but it also gave you an image back. So they were smart enough to pick a URL like that. So they actually did see the image, which was very clever. So you didn't even get an error. You just saw the image and you couldn't tell anything was wrong, but you did get hit with an attack. So yes, very elegant by 2009 standards. Okay, that's CSRF. So again, there's a lot of kind of moving parts, but it's really as simple as this slide right here. You trick the victim into making a request. They make the request. They automatically send cookies, and that's it. So it's literally just automatically sending cookies attack. Okay. Now there's lots of different ways to get this attack to work, but that's the base of the attack. So let's try to defend against it. Now, most of the CSRF defenses are implemented by the server, not the browser. Kind of weird, but if you think about it, it kind of makes sense because who is responsible for checking that this request is a valid request? I would say the server is responsible for that. So even if the browser is strict into making a request, if the server can tell that this was a CSRF request, then the server can stop it and say, nope, this is an attack. I'm not taking this. And that would stop the attack. So the server is going to implement these defenses. And you as computer programmers will find this relevant because you might be writing your own web servers and you need to make sure you have CSRF defense on. Okay. The first defense is the most powerful one, and it's the one that almost everyone uses today. It's called CSRF tokens. And basically it says one secret value wasn't enough. So just having that session token is not good enough because it will be automatically attached, and we saw how that goes wrong. So let's put another secret value in the request that the attacker doesn't know. This secret value only persists across a single request, and the server will only accept the request if it has the token and the secret. So we're adding a second secret, and we'll see how this helps in just a moment. But basically the idea is if you don't know both secrets, you can't create the malicious request. I guess you can create the malicious request even if you don't know the session token, right? So way back here, if I don't know the session token, I can still do this. I can just say make this request. The user will attach the session token for me. But now what we're saying is that this request here actually requires a secret as well. So I can't even tell the user to make the request because I don't know what the secret is. So I'm adding a second secret inside, and that's going to stop CSRF attacks. So this secret is called the CSRF token. It's a secret value provided by the server to the user. It's not a cookie. If it was a cookie, we would be back to the situation from before. But what we do is we require the user to give me that same value back in order for the request to be accepted. So it needs to not be sent in the cookie. We can send it in a header, a get parameter, post content, a form field. There are lots of different places, but it cannot be in the cookie or else we're back to the scenario from before. So it needs to be inside the request. So in the HTTP header or the HTTP parameter or the HTTP content. But it needs to be inside the request so the attacker doesn't know how to make the request. And this token usually is only valid for 1 or 2 requests, so it switches around a lot. Okay, here's a wall of text. I could talk about it or I could just show you the picture because I thought of this and I thought this was nice. So I guess if you're studying, feel free to use this, but here's a picture that makes it nicer. So let's do the attack with tokens this time. So here we go. I log into the server, same as before. The server gives me the session token, and now we both have session tokens to communicate. Okay. Now, before I make the request, so before I transfer money or before I buy something, I have to ask the server for another token. This is the CSRF token. This should probably say CSRF token. So now I'm going to ask the server for a CSRF token, and it comes back in the request. This is not a cookie. This is in the request. Okay, so I asked the server for a token. I received a token. So who knows the token? The user knows the token. The server knows the token. Nobody else knows the token. Now, if I want to make a legitimate request, I have to attach the token inside the HTTP request. So the token has to be in the request. It's not a cookie. It has to be inside the request for this request to go through. Now, what if the attacker wants to be like, make this request? Well, what happens is the user makes the request, but guess what? This request came from the attacker. The attacker doesn't know the token, so this request will fail because it doesn't have the right token inside. And the attacker doesn't know how to tell the user to include the right token because the user is not going to include the token. It's just going to do what the attacker says to do. So for example, remember the get request thing? So remember this? Maybe the token has to be sent as a parameter here. So it's like amount 100 to Mallory and CSRF token equals blank. Well, if the attacker was trying to do the image source tag, it would not work because they don't know how to put the secret here. So this secret is no longer automatically attached by the browser, even if the attacker doesn't know it. The attacker must supply it inside the request that is tricking the user to make. But the attacker can't do that because they don't know the secret. So that's how CSRF tokens work. Is I add an extra secret that the attacker doesn't quite know. Any questions on this? Because this definitely takes a bit of wrapping your head around. You're like, wait, why does adding a second secret work? But it kind of does. So maybe take a second to like try and internalize it or ask any questions if it doesn't make sense. It definitely took me a while. So, and one way to do this automatically for post requests is to use a hidden form field. So if you have a form, it has all these different fields, and you can add a hidden one that's in the HTML but not visible to the user. So that's one way to do it. So it's like a very creative, but also kind of janky defense because, again, all of this stuff was added on afterwards. So it looks kind of strange, but it did work. So it does work. And most people will recommend using this. There are some other ones. So this one is less good, but you can still use it. It's called the referrer header. So the idea is the requests in a CSRF attack usually come from a different website. Does anyone remember what this stands for? It's cross-site request forgery. That means that the request is coming from a different website. So let's think about this, right? If you were doing that IMG HTML tag thing, the request is coming from the form, right? You are making that request while you're on a web form. That's a pretty weird place to make a bank request. Like, why would I be talking to the bank while I'm on a web form or while I'm on Facebook? Or if I'm on an attacker's website and the attacker's JavaScript makes the request, I'm making this request from the attacker's website. Why am I accessing the bank from the attacker's website? That's pretty strange. So one way to kind of tell the difference is called the referrer header. This is a header in the HTTP request. So the HTTP request has a lot of metadata. One of them is called referrer, and it tells us, where did this request come from? Did they make this request while on a form? Did they click on a link? Did they do so on the attacker's website? Did they do so from the same website? So you can kind of figure out where they make this request from and take a guess as to whether it's an attack or not. And yes, this is a typo because web people, everything is so designed after the fact that someone misspelled refer and nobody fixed it. And now it's just called refer with one R. Cool. But again, the idea here is that you look for requests that came from legitimate websites as opposed to requests that came from strange places like forums or the attacker's website. So if the request came from the same website, so for example, if it's a login request and it came from bank.com/login, that seems like a very legitimate request. If I'm logging into the bank legitimately, I would do so by typing it on the bank login page. But if I make a login request from a forum or an attacker's website, that makes no sense. So I'm going to disallow those. And I'm going to reject those. So the server will look at the header that the HTTP request attaches that tells us where this request came from and accept or reject depending on whether that site seems like an expected place where someone would make a request. So that seems like a pretty good defense. There is a problem though. The referrer header kind of leaks private information because it tells you what website you were on before. So you may not want to tell people what website you were on before you made this request, right? Like, do you really want to tell me where you were before you came to lecture? I don't know. Maybe you do, maybe you don't, right? So it could leak private information. For example, if you're a top secret Apple developer, maybe you were on this website, corporation.apple.com/project/iPhone/competitors. I probably don't want to put this referrer header on a request to like the bank or something because now the bank knows that I work for Apple and I'm developing an iPhone competitor or something. That would be bad, right? Or maybe if I make a request to an advertiser, the referrer header will tell me where I saw the ad. Now I'm telling the advertiser information about myself. That doesn't feel good to me either. I don't want to do that. So a lot of browsers or company firewalls or security applications will actually remove the referrer header so that your privacy is preserved. So I think Firefox has a setting for this where it will just strip the header so that the referrer header is always blank. And that is just to make sure that you're not leaking information to people, right? You don't want to tell everyone what your last website was. That seems not great. So the browser will protect that for you. This also means the referrer header is not required. It's optional. So what if you are defending against CSRF and you get a blank header? What, right? Well, if I get a header with the same site, that's easy. Allow it. If I get it from a different suspicious site, disallow it. That's easy. What if it's from the same site? Or what if it's not, like it's blank? What do I do? Do I allow it? Well, now someone could be doing a CSRF attack with a blank header. Do I disallow it? Well, now maybe I'm denying legitimate requests. I don't know. Fail-safe defaults, security principles. I don't know. Do you know? I don't know. It's confusing, right? So referrer headers are good, but they're not perfect because there are lots of blank referrer headers and you don't know what to do if you get a blank referrer header. It depends. Okay. The final defense is a little bit new and kind of newfangled, so I'm not going to talk about it too much. But basically, cookies have another flag, so there are lots of different ones we didn't talk about. One of them is called same site. This basically says
the cookie will only be sent if the domain of the cookie exactly matches the domain of the origin. So not only are we checking the cookie policy from earlier, we're actually going to look for exact matches. So if you set the same site attribute to be strict, it will actually only send exact matching cookies. So for example, if evil.com causes your browser to make a request to this thing, the origin domain doesn't match the cookie domain, and so it kind of doesn't work. This is kind of a newfangled defense, and I wouldn't worry about it too much. And in fact, a lot of browsers don't allow this yet. I think that's kind of outdated. I think more browsers do use it now, but it is a little bit like new, so I won't worry about it too much. In fact, I don't even know if I understand it fully myself, but I think the discussion does talk about it. So if you're curious, you can stick around or something. But this is a new defense. The two main ones that you should know about are CSRF tokens, because this is the best one. It is really good because now the attacker has to guess the token, which they can't do, or the referrer header, which is almost good but doesn't work if the header is blank. And then this one's kind of new, so your mileage may vary. Okay, we've reached the end. Another spectacular timing effort by yours truly. So we talked about cookies. These are pieces of data to store state across multiple requests. So the browser server sets a cookie for you, you store it in your cookie jar, and you send it so that you can save state like dark mode, or I want to stay logged in. And those are things that let you associate multiple HTTP requests together. There are a bunch of attributes. There's name, value, domain, path, secure, HTTP only expires. Some of these are for security, like these two. Some of these are for the policy, like these two. The expiry date tells us when to stop eating the cookie. These are all useful attributes. There's a cookie policy. Remember these. These are super boring rules that tell us when cookies are relevant. So follow the rules, put them on your cheat sheet, and you're good. Then we talked about session authentication. We talked about how you can associate requests with an authenticated logged in user by saying the first time, enter your username and password, get a token as a cookie. In the future, the browser will automatically attach the session token cookie so that it knows that all those requests are from you, and you don't have to repeatedly enter your username and password. So this is the wristband session authentication method, right? And remember, you have to be careful about your tokens, because if someone steals your token, they can log in as you. So you need to be careful about that. The token should be randomly and securely generated, and you should not be sending these to the wrong place. So use cookie policy to check that your tokens are being sent only to the right places. Then we talked about CSRF. Lots of different details here, but the main idea is you are exploiting cookie-based authentication. So the user authenticates to the server, you trick the user.
Any better? Yes? I will assume so. Okay. That was exciting. Not really. Okay. CSRF really quickly. Again, a lot of moving parts, but the basic idea is you are exploiting cookie-based authentication where the browser automatically sends cookies. So what you do is the attacker tricks the victim into making the request, and the victim will automatically attach the cookies, and the server will accept it because it has the right cookie inside. So that's the problem. And the main trick in CSRF is I have to find a way to trick the victim into making the request. I can tell them to click on a link, or put an image tag on a form, or use JavaScript. There are lots of different ways, and you should just pick one. So that's CSRF. Then we talked about defenses. The best one is CSRF tokens, because you add another secret value. Now the attacker can't trick you into making the request because they don't know what the secret value is. So they can't include the secret value in their trick. And so their trick will fail. Or you can use referrer headers and see where did the user come from. If they came from a good place, accept it. If they came from a very suspicious place, don't accept it. This header could be blank though, and that could be a problem. And finally, there's a kind of new-ish defense called same-site cookies. So only send the cookie if the domain of the origin matches the domain of the cookie. And it's not fully implemented yet, so your mileage may vary. Okay, now that brings us to the end. Definitely had to speed up a bit at the end, but I think we made it. Are there any questions? There are a couple, so let's take a look. Someone said, can the CSRF token be brute force? That's a very good question. Thank you for catching me on that. So what you do with CSRF tokens and session tokens, honestly, is you make them long enough that they can't be brute forced. So remember how we said in crypto that if your key is 128 bits long, it will take the lifetime of the universe to brute force the key. Right? That was the thing from crypto. So you do the same thing here with CSRF tokens or session tokens, which is you make them so long that it's hard to brute force. So a usual CSRF token is probably around 256 bits, which, as we saw from crypto, 256 bits takes like the lifetime of the universe to brute force. That's a very good question. So you do make them long enough to avoid brute forcing. And you want to make sure that the PRNG or whatever you're using to generate the randomness is also secure. So you have to be careful. Cool. Any other questions? Okay. Either everyone is really confused or has spaced out, which is okay. I'll stop the recording though, and I will see you all, not tomorrow, tomorrow's Friday. I'll see you all Monday. So go enjoy your weekend. Think a little bit about Project 2, please. I know like whenever you're out there partying, do think about your design of it and then send us a draft by Wednesday. Okay, bye.